But before you start your actual analysis, we need to reflect a little bit on how do we actually choose between different statistical criteria? How do we choose between different statistical tests? And before we take a look at different statistical tests, we need to find some way of organizing them in a logical sequence. There are three characteristics that we need to be aware of when we are choosing a statistical test. First of all is the task, our goal. And today we will discuss three different goals. How can we compare an observed distribution with an expected distribution, or compare two empirical distributions, or compare several empirical distributions at once. And when we'll be looking at those statistical criteria that can solve those problems, we will also make important distinctions between independent and dependent samples and between non-parametric and parametric tests that we can apply. So what are all those things? For tasks, we will discuss slightly later when we approach them. But what is the difference between independent and dependent or related samples? It's very straightforward. We have independent samples when we have two or more groups of observations, and there is no pairwise relationship between observations in those groups. So for example, you have a group of male individuals and a group of female individuals, and these groups have different sizes, and all those individuals are not related to any other in any way. These are independent samples. And this is the situation that we have most often. However, sometimes we have a different situation. Sometimes we have samples where observations are related. They can be matched on a one-to-one basis. For example, you have scores on anxiety from husbands and from their wives. In this case, there is a pairwise relationship between these scores. Or you have scores for the same individuals measured at different points in time, before your experiment and after your experiment. Then again, for every individual Ivanov, Petrov, Sidorov, you have a pair of values which corresponds to his score before and after. Or you have a set of expert ratings, and there also you have different objects, and for different aspects you have ratings of the same objects. So there is again a pairwise association. These are the most frequent types of dependent or related samples. Why is it so important for us to make this distinction? Well, because depending on your type of your samples, you need to arrange your data in your statistical software in slightly different ways. And you need to choose slightly different tests that will have different expectations about the way you should arrange your data. So if your samples are independent, there is no pairwise relationship between them whatsoever. And if they are dependent, they are related somehow, like this nice couple of penguins. In case if you have independent samples, normally you arrange your data in two columns. One of these columns is a grouping variable which determines which sample does this observation come from. For example, if you have a group of male individuals and a group of female individuals, the grouping variable will be gender or sex. And the target variable is the variable which measures some kind of property that you're interested in comparing. So in SPSS or in any other statistical package, like Jamovi or R, your data are going to be arranged like this. A grouping variable and a dependent variable or a target variable, for example, anxiety. In case if your samples are dependent, in case if they are related, then your row in your data matrix corresponds to the basis for this relationship. For example, your row is an individual and each column is a measurement at different data points. or each row is an object and your columns are ratings by different experts, or your row is a family and your columns are score of a husband, a wife, and a child, and so on. So your data in SPSS look like this. For example, in the first example, we have repeated measurements. So for the same individuals, numbered here 1, 2, 3, 4, and they can, of course, have identifiers and other properties. We have 3 columns: anxiety time 1, time 2, and time 3. Or if your unit, your observation is family, like in the second example, your case is family, then these are also dependent samples. And we'll take a look at different tasks a little bit later on. However, before we take a look at those tasks, we also need to be aware of another property of our data that we need to estimate correctly, and that we need to inform SPSS or another statistical package about. This is the level of measurement. If you remember, in our fourth session, we discussed the measurement, and we discussed that we might have nominal scales where attributes are only named and there is no quantitative relationship, like, for example, preferred color or the brand of car that a person has. There are also ordinal scales where attributes can be ordered, like primary, secondary, and high education that a person might have, but we don't know exactly what is the difference between different levels, and for different individuals this difference can be quantitatively different. And there is also an interval scale where there is a unit of measurement, and a ratio scale which has an absolute 0. Now, if for ratio and interval scales, this distinction is usually not so important for our statistical analysis. That's why in SPSS they are jointly called scale. In Jamovi, they are jointly called continuous, but whether our data are nominal or ordinal, sometimes ordinal are also called ordered categorical in some statistical packages, we need to set this level of measurement for every variable. In R, nominal is a factor and ordinal is an ordered factor. So in R, we also need to set the type of variable correctly. And in SPSS, we do it just with help of graphic interface like this. So when you enter your data in SPSS, be sure to set correctly your measurement levels, because the choice of statistics that you will have will depend on these levels of measurement. And what happens if we don't set the level of measurement, or if we misapply statistics? If your scale is interval, and you apply some statistic that assumes an ordinal scale, you don't have any problems. Your results will be correct, but you will lose statistical power, because your statistical test will not use all the information in your data. However, an inverse situation, when you have an ordinal scale, but you treat it as if it were interval, this may be a bad idea, because your statistical procedures will be making assumptions about your data that are wrong, that are not supported by the nature of the thing that you are measuring. And as a result, you might have biased or misguided conclusions. That's why it's best to choose a statistical test that corresponds to your level of measurement. And that's why we also make a distinction between parametric and non-parametric statistics. When we say parametric, we usually mean statistics that assume a normal distribution, because in order to define a normal distribution, you only need 2 parameters, mean and standard deviation. And these parametric statistics, they also assume interval scale. They are easier to calculate, easier to apply, easier to calculate effect sizes for. And if you need to compare data with other studies or across different samples, usually it's better to use parametric statistics, because most people are using them as well. However, it only makes sense to use them if your data is close to normal. If your distributions are not normal, or if your sample is too small for you to be able to say confidently whether your distribution is normal or not. Because in small samples, just by chance, distributions can be very strange. Or you have an ordinal scale. Then you need to apply non-parametric tests. And in the following discussion, we'll differentiate between parametric and non-parametric statistics in order to inform our choice. Of course, non-parametric statistics is not the only solution for non-normal distributions, for strange, difficult situations. Nowadays, many statistical packages offer us another possibility, resampling techniques. We can use tricky procedures with our data when you have a sample of, for example, 100 individuals, and your distribution is strange. It's not normal, and you don't even know what theoretical distribution it corresponds to. Then what you can apply is called bootstrap. You draw repeatedly many very small samples from your sample, and you calculate the statistic that you are interested in many times in those different samples. And as a result, you obtain a parameter distribution for this particular statistic that you are interested in. And you can use this general distribution to evaluate significance of your statistical test. So bootstrapping can solve the problem of unknown distributions, distributions with unknown properties, or sometimes of small samples. However, with small samples, we need to be very careful, because if your sample is small, it might also be non-representative. And if it's non-representative, bootstrapping might be making misleading assumptions. So even if your sample is small, in order for bootstrapping to help you, it needs to be representative. But these are already advanced level issues. I'm not going to discuss this in detail, but just in principle, if you see bootstrapping somewhere in the literature, this is what it is. A generalized type of inference that tries to get rid of any distributional assumptions by drawing repeated samples from your dataset. So now that we know those principal important differences, let's explore different statistics that can solve different tasks.